Hello everyone, myself Lokesh Soni and I am working as an assistant professor in a EC department of AKG EC Ghaziabad. The topic of the today's lecture is binary arithmetic and Boolean algebra. In previous lecture we have seen the 1's complement, 2's complement, and now the content of this lecture is, first we will see complement for the other number systems, then Boolean laws, logic gates, representation of the Boolean expression like in SOP and POS form, and minterms and maxterms and truth table. So the complements for the other number system, like if we want to perform the tens complement. So in the tens complement, we have to subtract the numbers first from 9 and then add the plus 1. So it will generate the tens complement. As we can see from this table, the binary number, the radix or the base is 2. So to get the 2's complement, first we will perform the 1's complement and we have to add it 1 into it. Similarly for decimal, the base is 10. So to perform the tens complement, we have to first do the 9's complement and plus 1 into it. Similarly for octal and hexadecimal. So if we want to perform the 9's complement of this given number 20 minus 10, as I have already discussed in the previous lecture, a minus b can be written as a plus 9's complement of b, that is 10. So in the 9's complement, what we have to do? We have to just subtract each digit from the 9. Like 9's complement of 10 is nothing but subtract 1 0, that is 10, from 9 9. So it will give 9 and 9 minus 1 is 8. So 89 is the 9's complement of the given number. Now we have to add 20 plus 89, that is 20 plus 9's complement of 10. So it will give 9 and 1 0, 9. Here we can observe that carry is generated. So like in the case of 1's and 2's complement, if carry is generated, we have to add this carry again back to the result. So carry is 1 and result is 0 9. So if we add 1 into the result, we will get 10. So 20 minus 10 is the 10. So we will get the correct answer by doing the 9's complement. Similarly, if we want to perform the 10's complement, so 10 minus 20 we can write 10 minus 10 plus 10's complement of 20. So to perform the 10's complement, first we have to perform the 9's complement and we have to add 1 into it. So it will give the 10's complement. So 10's complement of the 20 is nothing but, first we have to perform the 9's complement, that is we have to subtract 2 0 from the each digit of the 2 0 from 9 9. That is, if we take the 9's complement of the 20, we have to subtract each digit by 9. So 9 minus 0 is 9, 9 minus 2 is 7. So 79 is the 9's complement of the 20. Now to get the 10's complement, we have to add 1 into the 9's complement. That is, we have to add 1 into 79. So it will give 80. So 80 is the 10's complement of the 20. Now we have to add 10 plus 10's complement of 20. So if we add 10 and 80 is the 10's complement of 20. If we add these two, we will get 90. Since there is no carry generated, so answer is negative. So as we have discussed in the 1's and 2's complement form, if carry is not generated, answer is negative and we have to take the 10's complement of the result. So again we have to take the 10's complement of the result, that is 90. So to perform the 10's complement, first we have to subtract the each digit by 9 9. So 9 minus 0 is 9, 9 minus 9 is 0. We will get 0 9. This is the 9's complement. And to get the 10's complement, we have to add 1. So the answer is minus 10. So 10 minus 20 is minus 10, and we are getting the same by performing the tens complement. The next topic is basic Boolean laws. So there are certain properties of the binary that we have to follow while performing any operation. Like 0 plus a in binary is a only, 0 into a is 0. This is an important property of 1, that is 1 plus a equal to 1, not a or 1 plus a, because in binary if 1 plus something is given, it is always equal to the 1 only. So 1 plus something is always equal to 1, and 1 into a is a. The complementary property says that a plus a bar equal to 1 and a into a bar equal to 0. That means if we add the number and complement of that same number, it will give the 1, and if we multiply the complement of the number with that number, it will give the 0. Next property, identity property, that means a plus a is always equal to a, not 2a. So in a binary numbers or in a binary Boolean algebra, if we add the same digit by multiple times, like 10 times, 20 times or etc., it will equal to only a single time, like a plus a plus a plus a is always equal to a only. This is always equal to a only. And a multiplied by a is also equal to a only. In absorption law, a plus ab equal to a. That means if we take a common from these two terms, we will get 1 plus b. And we have seen that 1 plus something is 1 only in the binary. So it will nothing but equal to a. Similarly, from here, if we open the bracket, a into a plus ab, and a into a is nothing but a only, and if we take a common from this, we will get a. Again, the distributive law says that a into b plus c is nothing but ab plus ac. Just we have to open the brackets. A plus bc, this is an important property. A plus bc can be written as a plus b into a plus c. And involution property says that if we take the complement of the number 2 times, it will nothing but the original number. Means double complement of a is nothing but equal to a only. Next property says that a plus b equal to b plus a and ab equal to b plus a, then it will follow the commutative law. In the associative law, a plus b plus c should be equal to a plus bracket of b plus c. De Morgan's theorem, this is a very important theorem. It says that a plus b whole complement can be written as a complement into b complement. Similarly, a into b whole complement can be written as a complement plus b complement. Principle of duality. Duality is nothing but we have to just replace the zeros by ones and plus by multiplication. Like if we have some number like 1 plus a, so in duality we have to replace 1 by 0 and plus by multiplication sign. So this is nothing but a dual. 1 plus a dual is 0 into a. These are the basic logic gates. First is the NOT gate. In NOT gate, if we are giving 0 here, we will get 1, and if we are giving 1 here, we will get 0. So it just complement the input at the output side. So the expression for NOT gate is y equal to a bar. Whereas in the AND gate is nothing but multiply the two inputs. So it will only 1 when both the inputs are 1. So the expression for the AND gate is y equal to a dot b. Whereas OR gate just perform the addition of the two inputs. So OR gate output is 0, possible only if both the inputs are 0, and the expression for the OR gate is A plus B. Apart from that, there are gates which are called as universal logic gates. NAND and OR are the universal logic gates. Why these are called the universal gates? Because with the help of NAND and NOR gates, we can implement any logic gates. Like with the help of NAND gate, we can implement the, here you can see, with the help of NAND gate, we can implement the NOT gate. With the help of NAND gate, we can implement the AND gate. With the help of NAND gate, we can also implement the OR gate. So with the help of NAND and NOR gate, we can implement all the basic logic gates. That's why these two are called as universal logic gates. Output of the NAND gate is nothing but the complement of the AND gate. In the AND gate, we have seen that output y equal to A dot B. So in the case of NAND gate, the output will become A dot B whole complement. So if we are giving 0 at 0, complement of 0 is 1, so output is 1. If we are giving 1, 1, output is 0, because we have to take the complement of that. For NOR gate is nothing but the complement of the OR gate. That means A plus B whole complement. There are, apart from that, there are two gates, XOR and XNOR. XOR gate is known as exclusive OR, and the expression for the XOR gate is A bar B plus AB bar. So for the same inputs, the output of the XOR gate is 0. As we can observe from this table that for the same input A and B, the output is 0. And for the distinct inputs, the output will be 1. Whereas in the case of XNOR gate, for the same input, output is 1. And for the different, output is 0. So it will, XOR and XNOR are nothing but the complement of each other. Next is the representation of the Boolean expression. There are two kinds of the representation in which we can represent any Boolean function. One is sum of product. Why it is called sum of product? As we can see from this example, AB plus AC. That means AB is the product, AC is the product, and we are doing the sum of these two terms. That's why it is known as sum of product. Second, we can represent in the POS, product of sum form. Product of sum, that means these two are sum and we are doing the product of these two summation terms. So it is nothing but this is sum and there is a product. So this is known as the product of sum. Next is the canonical representation. If we want to do some minimization of any Boolean function, first using the K-map or other that will come into upcoming lectures, first we have to convert any terms into a canonical form. So what is canonical form? Canonical form means each and every term must contain each and every variable. For example, if I have any expression y equal to AB plus BC. So how we can convert this into a canonical form? So in canonical form, let's say this y is a 3-variable function A, B and C. So canonical form means each term must contain each and every variable. Like in first term there is AB, C is missing. In second term, B and C is present, A is missing. So to convert into a canonical, AB into, we have to add C plus C bar. Why we add C plus C bar only? Because C plus C bar is 1. So if we are multiply some number with the 1, it will the original number only. In second term, A is missing, that's why I have to add A plus A bar to convert into a canonical. So now just open the bracket, so it will become ABC plus ABC bar plus ABC is already there, so we need not to write it again. So we have to write A bar BC. So this is the canonical form of this given expression AB plus BC. Next is the truth table, min terms and max terms. So what is min terms and what is max terms? Let's say we are giving some table with the values of A and B are 0, 0, 0, 1, 1, 0 and 1, 1. So, and let's say Y is given 0, 1, 1, 0. So, for the first term A and B are 0, that's why I have written A bar and B bar. For the second term A is 0, B is 1, so I written A bar and B. For third term A is 1, B is 0, so we have to write A, B bar. And for the fourth term A and B both are 1, so this is A and B. Whereas in the max term, for the 0 we have to write same number, we don't need to take complement for the max term form. For the max term, if 0 is given, we have to write A only. If 1 is given, we have to take the complement of that variable. So max term and min terms both are in a complement in nature. So here we can observe that A and B both are 0. So in case of the max term, we will write A plus B, because min terms are generally in the form of SOP, sum of product. Min terms are in form of SOP. Whereas max terms are in the form of POS. So that's why in max term we have to write in the form of POS, that is product of sum. So we have to add the bits. Whereas if we see 1, 0, 1 we have to write A bar and 0 we have to write B only. So A bar plus B. So that's how we have to represent any function into a min terms and max term forms. Now for the 3 variable truth table, this is a 3 variable truth table, A, B and C, and Y is the output. As we can see that Y will be 1 at 2, 3, 5 and 6 places. So in case of the min terms, we have to take the combination at which output is 1. So to fill the min terms are represented by sigma m. Sigma is represent the sum and m is represent the min terms. So in case of the min terms, we have to take the combination at which output is 1. So output is 1 as 2, 3, 5 and 6. Whereas in the case of max terms, it is represented by pi m. Pi represent the product, because max term are represented in product of sum form, and capital M represents the max term. To write the max term, we have to take the combination of 0. That means at the output, we have to note it down the terms where the output will be 0. So output is 0 at 0th place, 0, output is 0 at 0, 1, 4 and 7. So max terms are 0, 1, 4, 7, because at these bits are to be 0 in for the outputs. So in case of min terms, we have to write the terms which are containing the 1. For the max term, we have to write the terms which are containing the 0. So that's how we have to represent any function into a sum of product and product of sum. For example, let's say I have some expression y equal to let's say I have in terms of the min terms like 0, 2 and 4. Then how we can write 0, 2 and 4? Since this is a min terms form, because this is a sigma and this is a small m. So these are the min terms form like 0 to 4. That means at the 0, 2 and 4 the output will be 1. So if we write this into a form of the variable, let's say this is a 3 variable a, b and c, then 0 will be written as a bar, b bar, c bar. 2 will be written as a bar, b, c, and 4 can be written as a, b bar, c bar. This is equivalent to 0, this is equivalent to 2, this is equivalent to 4. Whereas if we want to write the max term, let's say y is equal to given as pi m, and the max terms are given as 1 and 3. Since max terms are in the form of product of sum, so 1 will be equivalent to binary of the 1 is 0, 0, 1, binary of the 3 is 0, 1, 1. So for the in max term 0 can be written as without complement like a plus b, but for the 1 we have to take the complement, that is c bar. For the 3, 0 we have to write as it is. For 1 and 1 we have to take the complement of the bits like b bar plus c bar. So that's how we have to represent any numbers into a SOP and POS form if we have given the min terms and max terms. So that's how we have to write in terms of the variables. So that's how for this lecture, and there are some reference books that you can follow like Morris Manon. This is a standard book for the digital design, and RP Jain and A Anand. So these are the standard books from which you can refer these books for further. So thank you all for listening, and we will continue in the next lecture. Thank you.